Okay, in this problem, I've got a 50-pound wheel that has a radius of gyration of 0.7 feet. Okay, basically, if it rolls without slipping, I want to determine the angular velocity after it's rotated to clockwise 90 degrees. Okay, it starts at rest. So basically, this spring has an initial stretch in it, pulls it to the right. Okay, the spring has an unstretched length of 0.5 and a K as shown there. So first thing I want to figure out is basically how far it's going to roll for 90 degrees. Okay, again, that 90 degrees is pi over 2 radians. Okay, this thing has a radius of 1 foot. Okay, so it rolls pi over 2 times 1 feet. That's the center of gravity, rolls that far. Okay, then B actually rotates down, so I have to add another half foot to that. So the length of the spring at the end of rotation is 0.9292, based on how much it rolls, which is pi over 2 times the radius plus that half a foot that I've got included there. Okay, so using that, I'm going to use the conservation of energy, because the only force acting here is that spring force. Remember, rolling without slipping, the friction does no work at all. Okay, so the spring's the only thing doing work here. So starts from rest, so that's where this 0 comes from. And this is 1/2 K S squared, where this is the stretch in the spring. This first is the actual length of the spring minus the unstretched length of the spring here, right? This is that triangle, 1/2, 3 feet to find, Pythagorean theorem to find the length of the spring minus the unstretched length. So that's the initial potential energy. Okay. Finally, okay, the kinetic energy. I have initial kinetic energy. Okay, where this is 1/2 I omega squared, where I is given by the radius of gyration and the mass, which is the weight divided by 32.2. This guy here is 1/2 mv squared, where it's 1/2. This again is the mass. This is the velocity of the center of gravity, which again is the radius of 1 times omega, all of that squared. So again, I have to include both the rotational part, 1/2 I omega squared, plus the linear kinetic part, the translational, which is 1/2 mb squared. Okay, but both of those are related to omega as shown here. Okay, I do have some final potential energy I need to include as well, and that is just 1/2 K S squared, where X is the new length of the spring that we talked about previously, minus the 0.5, which is the unstretched length of the spring. So I've got this big, huge equation. The only unknown in it is omega. I can solve for omega, it's 1.8. So again, conservative forces, only springs acting here. So I just take the initial kinetic and potential, set it equal to the final kinetic and potential, solve for omega.